All right, section 3.5 has a word in it that I just used, and you guys all kind of cringed back in chapter 1. What was the word? Limit. Well, it was limit, yeah. This has a word infinity in it too, but it said limit in it. So this section is about limits at infinity. And first I want to talk to you about what that means, what we're referring to by limits at infinity. So limit of infinity, so let L be a real number. The statement, the limit as x approaches 0 of f of x equals L, means that for each epsilon greater than 0, there exists a capital M greater than 0, such that f of x minus L in absolute values less than epsilon whenever x is greater than M. It should look really familiar. I'm not going to make you memorize this one. Okay, so just write it down and then I'll explain what it's saying. The second piece is almost the same as the first one, except that you have a capital N and it says less than instead. What's going on here? Well, what's really going on here is this capital L is a number that's getting infinitely large. The capital N is a number that's getting infinitely large and negative. Okay? So if you imagine in terms of a graph, what it means to have a limit that is infinity is it means that, in fact, we'll even draw it in like an asymptote because that's where we usually see it happening. So say, for instance, you have this asymptote here, and let's say that it's at x equal 3, and the graph does this. Okay? And we're looking at the limit as, you guys love this, I know, but the limit as x approaches 3 from the left of our function, we'll call it f of x. We're going to say that this is going to equal infinity. Okay? We're going to say that it's equal to infinity if whenever we get close enough, let me shade it, I don't want that color though, not this one. Whenever we get close enough over here to the actual asymptote line itself, we have y values that are larger than we had before. Okay? So this is one issue. What we're seeing happening in this section is about asymptotes primarily. So I have one more slide and it's about horizontal asymptotes too. Okay, so this is a slide that's about vertical asymptotes primarily, right? We see this idea of getting infinitely large or infinitely small. If I flip this graph upside down, we've got this capital N business that we talked about before. So what it's referring to when it's referring to the capital M is that it's saying, okay, look, here's the maximum M line. I'm going to get bigger than that line. And that's really what this definition says. It's going to be above there. And if I did it below the x-axis, you know, as a negative value, it's going to get lower than that negative value. Okay, so it's less than n. That's what it's referring to. Okay? Okay, so take a look then at horizontal asymptote. So horizontal asymptote is the line y equal L is a horizontal asymptote of the graph when f of x, of the graph f, when the limit as x approaches negative infinity of f of x equals L, or the limit of f of x as x approaches infinity is equal to L. And I had a picture on the last slide that I could duplicate if we'd like here, and I will, because it works just fine. The part of the graph that I really care about at this point is the part of the graph that's over here on the left. It's leveling off at the y-axis, right? It's getting infinitely close to the y-axis, and in some algebra class somewhere along the way, you referred to that as a horizontal asymptote, and this is what it's referring to here as well. And this is saying that if you take this limit on this graph that I'm giving you the example of, the limit, and your x value is approaching negative infinity, what does it mean? Well, it means it's going left forever. If it said x value approaches positive infinity, it's going right forever. And if you traced along that graph as that happened, right, if you kept tracing along the graph like this, what would happen is you would be sort of tapering off or leveling off at a specific y value. So of course not every function does that, but there are some functions that do, right? Rational functions in particular do that. So this one we would actually say that it's approaching a y value of what? 0, because it looks like, at least the way I've drawn my picture, is that we're approaching the x-axis, which is y equals 0. Okay? So this is what it's talking about. And we have one more theorem. If R is a positive rational number and C is any real number, then the limit as x approaches infinity of c, that's a number, over x to the r is equal to 0. So anytime you have something in the form that's a number over x to a power, as x goes to infinity, that limit is 0. And as x goes to negative infinity, that limit is 0 as well. So it has that same sort of picture that I drew back here. It has this tapering off at the y-axis thing going on, either from above the y-axis, tapering off to the x-axis, either from above the x-axis or from below the x-axis, either way. But it's tapering off at the x-axis, which is y equals 0. And that will always happen if you have a constant. I'm going to say it again, a constant, okay, over x to a power.
Like x squared.
Yes, like x squared. And it doesn't even have to be x squared. It could be x to the power 1/2. That's still x to a power, right? What's another way we write x to the power 1/2? Square root. So if we had 1 over the square root of x, it would still have this property, right? And they tell you here it is a positive rational number. So that is important. So I used the example of 1/2, but we couldn't use the example of negative 1/2, right? Because that'd be negative. So it has to be a positive number, and it has to be rational. So we're also not going to say like x to the pi. All right, that's not how the theorem is set up to describe this. Okay. All right, so I'm going to show you how this works, how we apply all of these theorems in the context of a particular problem. So we have the limit as x approaches infinity, and we have h of x, which is the function f of x that's given 5x cubed minus 3x squared plus 10x, and it's over x squared. So the first thing we're going to do is we're just going to write all of this combined. We're going to replace the f of x in the function h of x with the function f of x. So 5x cubed minus 3x squared plus 10x over x squared. Okay, so far so good? Just a replacement. The next thing we're going to do is we're going to simplify what we have here. Okay? So how would I simplify that? If you were supposed to say we're not doing that on this problem, but if you were supposed to take the derivative of this and you didn't want to use the quotient rule, what could you do?
Put x squared as a negative, like x is.
You could, but then you'd have to do distribution after that. There's a simpler way to do it. I think cancel out would be better, but here's how I would suggest doing this. I know you guys have seen me do this before.
Yeah.
Right? It's sort of using, and it's not really in reverse, but it's reverse of how we normally use it. It's using the idea of getting a common denominator and combining things into a single fraction, but it's doing it backwards, right? You're breaking apart the single fraction into its individual components so that you can simplify them. So the first piece, how does the first piece simplify? It's 5x. How does the second piece simplify? It's 3. And how does the third piece simplify? 10 over x. Okay, so everybody good with it so far? All we did was do algebra to simplify. We haven't done any calculus yet. All right, the calculus that we're supposed to do is we're supposed to find the limit of this h of x function. So we're supposed to be finding the limit as x approaches infinity of h of x. That's the question that's being posed. And after we did our simplification, that's equivalent to asking the limit as x approaches infinity of 5x minus 3 plus 10 over x. Now, let's just focus on the end of this part first. If I did the 10 over x part only, according to the theorem that we had on the previous slide, what's the limit of that component only? That's 0. And the way that we usually sort of draw that is we draw, oh, that was not what I meant to do. That was way large. Hang on. Is we sort of draw, that was still too big. Oh my goodness. Let's try 6 point. Oh, that'll work. All right, so this is going to 0.
Draw like that.
Right? You usually draw a line through and draw it going to 0. It's one way that we do it. You can also break it apart into each component. I don't think you need to do that for me, but I have seen professors have them done that way before. So we take the limit of 5x, and we take the limit of the 3, and we take the limit of the piece at the end. Okay? Let's work our way backwards. So the last piece is 0. It's not equal to 0. The limit is 0, right? It's approaching 0. That's why I drew the arrow. I didn't just mark it out and eliminate it. I drew an arrow that showed that that's approaching 0. What about the 3? What is the negative 3 approaching? Negative 3. Constants, limits are constants. They don't change. So that one's negative 3. But what happened at the beginning with the 5x? That's infinity. Yeah? If you continue to put in larger and larger values and you multiply them with 5, you get larger and larger values. And there's no tapering off behavior there, correct? So if you want to think about it, what you're actually drawing is you're drawing this piece is going to 3, negative 3, and this piece is going to infinity. So what happens when you have something that's approaching infinity,
It'll be infinity.
minus a 3, and plus a 0? It's infinity. Infinity trumps it all, right? I mean, like, it takes precedence because it's bigger. Now, you have to be careful because if you had an infinity and a negative infinity in here, we'd have to sort of have a discussion differently, correct? We don't, so there's no discussion to be had. But this is actually infinity. What's that?
I think we'd have one on the board.
No, because I'll show you how to deal with it when those kind of things happen so that it doesn't end up cropping up. Okay? Any question on that?
No.
Okay, so our whole goal is to break the function apart into using pieces that we already know. That's what the goal is. Similar question, but notice that the denominator is different this time. We have the same numerator, I'm pretty sure, yeah? So we're going to replace it. It's 5x cubed minus 3x squared and plus 10x. But the denominator now is x cubed. Okay, so algebra first to simplify. What does this give us?
5x cubed divided by x cubed minus 3x squared divided by x cubed
It's still infinity.
plus 10x.
Are you so sure?
Kind of.
Let's take a look. Nope, you're doing it great, Christian, no problem. All right, what's the first piece going to simplify to?
5.
5.
Oh, never mind.
Ooh, what's the second piece going to simplify to?
0.
3x over, or 3 over.
3 over x.
I'm rushing.
Yeah, don't rush too fast through this. And then what's the last piece? 10 over x squared. Now, you do need to be careful. Don't go drawing your arrows here approaching zeros, because none of these things actually approach 0. It's the limit that does, correct? Okay, so we're actually looking now at the limit
Now,
as x approaches infinity of 5 minus 3 over x plus 10 over x squared. This is where we would draw our arrows in of what things approach. All right, so we'll go in order this time. What does the 5 approach at the beginning? 5. What does the negative 3 over x approach?
0.
0. And what does the 10 over x squared approach? 0. So what is the limit of this one?
5.
It's actually a constant 5.
Sweet.
Okay, so the denominator matters, like the exponent of the denominator matters, because sometimes it actually ends up giving you pieces that completely eliminate variables, like it did in this 5, right? And sometimes it leaves the variable either in the numerator or in the denominator, like the 5x in the last one, or like the 3 over x on this one, right? All right, now they're going to get a little bit different, because what do you notice happening in the denominator on this one that did not happen in the denominator on the last one?
Minus 1 to
Yeah, it got more pieces, right?
Yeah.
I can't just write one piece in the denominator that cleans things up and cancels things out. So what do I do now? Well, here's what you do. Nope, can't do the quotient rule because we're not actually taking derivatives, right? We're looking at limits. What did you say? Practice another version. All right. What I'd like for you to do is I'd like for you to look at what the highest exponent on x is. It's cubed. It's x cubed, right? And it is on the bottom. All right, so what we're going to do is we're going to multiply every component of the fraction by 1 over x cubed. So actually that's multiplying the numerator and the denominator by 1 over x cubed so that we get all the components, and we're allowed to do that, right? Because that doesn't change a fraction. Anytime you multiply a fraction by the numerator and the denominator by the same thing, that gives you an equivalent fraction. So this is a totally legit operation. I'm not really like making things up, I promise. Okay? All right, so what does that do? Well, it's going to give us a lot of fractions, obviously. The first piece we're going to get is 3 over x cubed. And then I'm going to get a 2x over x cubed. all over a 3x cubed over x cubed and a negative 1 over x cubed. Right? This is like exactly what you don't want to see when you're given a problem, is fractions inside of fractions. And yet that's exactly what we need to do in order to get the problem to be helpful for us.
It's kind of backwards.
Yeah, it's kind of backwards. Now, parts of this are going to simplify and clean up, and parts of it aren't. So like the very first piece is not going to do anything, right? I can't do anything to write 3 over x cubed any differently. It's just going to stay of 3 over x cubed, so I'm just going to rewrite it. What about the next piece, 2x over x cubed?
2 over x.
Yeah, it's 2 over x squared. All over. What about 3x cubed over x cubed? That's 3. And how about the negative 1 over x cubed? Can't do anything. Okay, everybody good so far? All right. Again, we still haven't actually done any calculus. We did some weird algebra, but there was no calculus there. The calculus comes in and applying this theorem that we had back over here to this problem now. Every component that you're left with that has a number over x to a power has a limit of 0, right? So that's 3 of them, isn't it? This piece, and this piece all approach 0.
Yes.
And what about my 3 at the bottom?
It's just 3.
It's just 3. So this ends up giving me truly, it gives me 0 minus 0 over 3 minus 0, and that is
0.
0. Now, what if I had gotten a 0 in the denominator?
Infinity.
Yeah, that's a problem, right? And it doesn't necessarily give us infinity or 0. We don't know. We need to go back and reevaluate. What probably happened is you divided by something that was too large. Right? Like if instead of multiplying by 1 over x cubed here, I want to multiply by 1 over x to the 4th. I'd have constants over x on all the problem parts, and that would give me lots of zeros, too many in fact.
So do we always take the highest exponent?
Yes.
And that's like we don't go over it.
Mhm. Right. Always the highest exponent. Bryson.
Why do we multiply by 1 over x?
We're trying to get zeros in as many places as we can. That's what we're really trying to do. And so most of the pieces don't have an x cubed in them. They have x to some lower power, and they will have a limit that goes to 0.
So you usually try to multiply by the highest power.
You always multiply by the highest exponent power. That's right. 1 over it. Yeah.
So 1 over the
1 over the highest exponent power. So write that in your notes if that's helpful to think about in words. 1 over the highest exponent power. So this one gives me a limit of 0. Okay.
Wait, so you said you had done 1 over x, what would happen?
You would have gotten a 0 on top and a 0 on bottom. And 0 over 0 is an undefined value, which means it could equal anything. It really means you made an error, is what it really means in a problem like this. You've multiplied by something inappropriately.
So it can equal undefined?
Well, I'll show you what happens when you have something undefined. I think I have an example later on. Maybe not. Maybe I lied. I don't. But if the only way you would get something undefined is if you had a number that was not 0 on top divided to 0 on the bottom. That would give you something that would actually be an undefined value, and then we wouldn't have.
The limit doesn't exist, or is that just like the issue there?
It's usually, it either means limits infinity or negative infinity is what it actually means. So if you ended up with, say, like if this were flipped upside down, if I've totally flipped this fraction upside down and I had 3x cubed minus 1 over 2 minus, or 3 minus 2x, I would have a limit of either infinity or negative infinity. That's what it would be. And what you would end up happening down here at the end is you'd get 3 over 0. Because it's not 0 over 0, you didn't mess up. 3 over 0 is a legit possibility. And for what we're doing, we can either say that it doesn't exist, or you could look more carefully by looking at the graph to decide, is it the infinity or is it the negative infinity?
So at that point, you would just use the graph.
Yes, you could. Mhm.
Okay.
Right. Because it would be one or the other.
Or just use graph.
Yeah, but if you're not going to show me the calculus part of it, then we're probably going to end up with some low scores on things, and I know that's not your goal. Yeah, probably not. Okay, a couple more examples. This one is different. How?
It's got a square.
It's got a square root in it. So if you were looking at this and you said, what is the highest power of x, you probably, prior to the fact that I just drew your attention to the square root, would have told me there's an x squared in it, right?
Yeah.
But that x squared is really underneath the square root. So what is really the highest power?
It's 1.
It's really 1. Okay? So let me show you how it works when we're looking at this one. We're going to multiply by 1 over x on top and on bottom, but I'm going to express it on bottom a little bit more helpfully. I'm going to multiply on the bottom by 1 over the square root of x squared, which is x, right, guys? Sure. I mean, square root of x squared is x. Why do I want to express it that way? Well, because unless they're both underneath a square root, I can't combine them.
Okay.
You with me? I need that over that. I mean, I need that square root involved, so I want to write it as the square root of x squared in order to combine it with the square root denominator to have.
You can just multiply that with the square root of x squared minus x.
You just multiply the whole denominator out?
Okay, say again, Bryson, I'm sorry.
So can you not just multiply the entire radical 1 over x squared minus x, multiply that times top and bottom?
Get rid of the radical.
You could. That would be another way to start the problem. I think you're still going to end up with a square root then in the numerator that you're going to have to clean up with either way. So somewhere you're going to have a square root, whether it's in the denominator right now or in the numerator later if you do that. Yeah. Okay, the numerator is very friendly. What happens when I multiply? In fact, we'll write it out just to be very clear. We're going to get an x over x in the numerator, right? Okay. The denominator, I'm going to have a square root, but then I'm going to have the x squared that's the beginning of the denominator right here over the x squared from here. Okay? And then I'm going to have the x, which is the second piece of the denominator, over the x squared, which is here.
Yeah.
Everybody see where those pieces came from?
Mm-hmm.
Yeah? Okay. Let's clean up what we can clean up before we actually, use the limit processes that we're learning right now. What does the numerator become? 1. In the denominator, what do I have?
Square root of 1 minus. No, 1
1 over x.
Right, 1 minus 1 over x. Okay? So that actually cleans up, like, really nice. Agreed?
Sure.
That's awfully pretty. There's only one place that still has a variable in it, the 1 over x part. And whether that variable 1 over x piece is underneath a radical or not, it does the same thing. What happens?
0.
It approaches 0. So this piece goes to 0 right there. So I have 1 over, and this one happens to be the square root of 1 minus 0. If it were the square root of 2, you can't just eliminate it. You'd have a square root of 2, okay? So this just happened to be 1, which is very friendly. So 1 over the square root of 1 gives me 1. Gives me 1. A lot of work for the number 1. It could be worse. We could have rationalized the denominator too. I mean, that would have been even more work, I think, because we still would have ended up with a radical in there, unfortunately, right? Yeah. Okay. The next one is about half of you guys' favorite stuff in the class.
Where you did the arrow,
Yes.
would you not have just done the arrow there for all of them?
Yes, you could have. I tend to only put personally, I tend to put the arrows on only the pieces that go to 0. Because constants don't change, so I don't draw the arrows on the constants usually. And this one only had constants and 0. But yes, you could have drawn, like Garrett's asking, could you have put the arrow on each of these and written down that they each went to 1? Sure, absolutely you could have. Yeah. If it helps you to see that, to think that you've actually considered all those pieces, you could do that. All right, so what's so much fun about this one? It's trig. So let's pretend for just a second that the numerator were just a number.
Can we take a 2 out?
No, you can't take a 2 out.
Dang it.
That's just like a trig, like cardinal sin of trig. You cannot take the angle and move it anywhere, right?
I want to move.
Right, because you guys know, I mean, you know that the sine of 30, and let's say the sine of 60 does not equal this 2 times the sine of 30, right?
Yeah.
Those are not equal. So yeah, you can't pull a number out of inside. This is sort of grouped together and they're stuck. They're stuck, okay? All right, so let's say for a moment that we did not have sine 2x on top. We had a constant. It was a 5,
Oh,
2.
cool.
I don't care, just a number. If we had just a number on top and the x on bottom, what would this limit be? 0. It'd be 0. Because what happens when you have 1 over 0? I'm sorry, 1 over infinity? Well, it's 0. This is the theorem that we had back here. What was its number? Oh, we didn't even have a number. The limit's an infinity theorem. This one right here. So if we had had a number on top instead of sign, this limit would be 0. Agreed? Okay, so that's important for us to realize. Second piece that is important for us to realize is that the sine graph looks like what?
A roller coaster.
It looks like a roller coaster. It looks like a wave. It looks like a bounded function. Where is it bounded between? 1 and -1, right? So all it does is it bounces back and forth, up and down between 1 and -1. Never gets further away than that. So it's not a constant, but it kind of is, right? It doesn't like get increasingly large or increasingly small. It keeps bouncing up and down between 1 and -1.
Yes.
So imagine, I'm going to do the math for this in a moment, but just imagine thinking about what the graph is doing. If you're bouncing up and down between 1 and -1, but you're dividing by something that's getting infinitely large, what's going to happen? Yeah, you're going to continue to bounce up and down, but the bounces are going to get smaller, right? Because you're dividing by something bigger, right? So like if x is equal to 1, you can go between 1 and -1, but if x is equal to 2 in the denominator, you only bounce between -1 and -1/2 and 1/2. And if x is equal to 10, you bounce between -1/10 and 1/10. And if x is equal to 100, you're bouncing between -1/100th and 1/100th.
Okay.
The bounces get tinier.
Yeah.
And they're all narrowing down like as you go out to infinity. And in fact, they do it very, very fast in your calculator. You almost can't see it happening. They bounce so quickly up and down between around that x-axis. They taper off very quickly. So we expect this to have a limit of 0. Are you guys with me?
Okay.
Okay. So let me show you how we actually think about this. What we think about this as, and this has actually got a name, it's called the squeeze theorem, is that the sign value is, sometimes called a sandwich theorem. The sign value is squeezed or sandwiched between two values. We've already said it's -1 and 1, right? So I'm going to write down that fact, that -1 is less than or equal to sine, and the 2x has absolutely no bearing on anything in this problem. It's just there. Okay? It doesn't change anything. But the sign value is sandwiched between or squeezed between -1 and 1. Agreed? Okay, very cool. So what we're going to do next is we're going to put all of them divided by x. I mean, we're allowed to do that, right? It's a triple inequality. You've probably worked with them before, maybe not substantially, but occasionally. As long as you do something to all the sides, you can do it. And it has to be an x value that's positive, but we know x is positive in this. Why?
Because it can't be negative.
It's positive. Positive.
That was awesome. I love that, Dawson.
I really meant.
What did you really mean? Say it differently for me.
I'm sorry.
No, you're fine. Say it differently.
In the definition thing, did it say that it had to be positive?
Nope, it didn't.
Dang it.
There's something else. Do you have an idea, Mooney?
It's positive infinity.
Because x approaches positive infinity. That's what you're going to say, Addison? Yeah, it's actually up here in the limit part itself. If the x value is approaching positive infinity, at least at some point the x values are positive, right? And those are the ones we really care about because we're eventually getting to the positive far right side of the graph. Okay, everybody good with that?
Did you like that?
I did like that. That was awesome. Okay, so again, just like we're able to divide each of those three sides of the inequality by x, we're also allowed to take the limit of each of the three pieces. Make sense? Sure. So we're going to do the limit as x approaches infinity of -1 over x. And we know that has to be less than or equal to the limit, as x approaches infinity of the sine of 2x over x, which is less than or equal to the limit as x approaches infinity of 1 over x. All good so far? Cool. What's happening on the left-hand side and on the right-hand side of this triple inequality? They are both 0. And I'll tell you what, if this side is 0 and this side is 0, we have squeezed the middle value and forced it to be between 0 and 0. And there isn't any values besides 0 between 0 and 0, right? Yeah, this is why it's called the squeeze theorem. So this is now squeezed or sandwiched between 0. So this limit right here resides between here. And it has no choice now but to actually be 0 as well. I tricked it.
That's nice.
Yeah, it's kind of like a trick. And that's called the squeeze theorem. If you can squeeze it between two values that are both becoming the same thing, then it automatically has to be the same thing as well.
Awesome.
Everybody good with that? All right.